Okay. Good morning, everyone. We're just gonna get started in a minute. Till then, sit back, relax, grab a glass of water. All right. Well, it's 10 a.m. in my clock, so let's begin. How are we doing today? How are we feeling?
Good, thank you. And you?
Not bad. Maybe I don't know. Give me like a thumbs up or like a reaction if everything's all right. Right. See two thumbs up. So okay, at least minimum of two people are doing okay. Oh, I see four. I see three. Great. Well, I hope by the end of the lecture we can all be with a thumbs up feeling. Anyways, we are delving into quantum mechanics, which is perhaps the most esoteric topic in the course, simply because we have to start looking at physics in a way that doesn't really represent the real world. Before we do that, though, I do want to quickly talk about units. So from now till, well, forever, you're going to have to deal with, measurements with all kinds of units, all kinds of magnitudes. So it's good to sort of get a notion of what each sort of prefix, like what milli, nano, micro, pico, all that means. And even though there's technically a lot of prefixes to sort of know, you all kind of follow a rule of thumb. So what I mean is just jump into this. Um, if you look at whatever units you have, you can always attach some prefix to it, like kilograms or nanometers or picoseconds, I guess. And for the most part, in physics, the prefixes that we use the most tend to be either bigger than unity or smaller than unity, of course. If you're bigger than unity, the prefixes tend to go up by 3 powers of 10. So if you have kilo, that's 10 to the 3. And then up from that is mega, which is 10 to the 6, giga 10 to the 9, and tera 10 to the 12. So you don't really have to necessarily memorize kilo, mega, giga, tera independently. You just kind of remember the order and that each one goes up by a power of 10 to the 3. If you're going below unity, then except for lengths which have the centimeter, which is 10 to the negative 2 meters, most of the prefixes are the milli, micro, nano, and pico, which, like the above unity prefixes, they are spaced apart by 10 to the 3, but now it's 10 to the negative 3 since they're getting smaller and smaller. So they're measuring smaller quantities. So yeah, it's just maybe the bigger confusion might be remembering the micro is bigger than nano. For milli, it's in the name milli, right? Mil implies like a thousand, so there's a hint. The way you can remember the difference between micro and nano is that Nano is 4 letters and starts with N and has two N's. So 9 is also 4 letters and has two N's. So nano 10 to the negative 9. That's one way to remember. And then maybe micro has, more letters than nano, so it's bigger. Anyways, it's just kind of worth to know the prefixes. If you keep studying physics and chemistry, you're going to save a lot of time if you can kind of look at a unit and know exactly what it is in scientific notation. Having said all that, I'm just going to jump into the tutorial for today. It's already up on Omnibox, so you can follow along. Let me just do a little bit of recap. For this chapter, we kind of talk about some things that new theories of physics can explain, but classical physics couldn't. So like thermal radiation, for example, which is just energy anything gives off, kind of depends on how hot it is. We as humans mostly give off infrared radiation at room temperature that can heat things up and they'll glow. They'll start to glow. And there's a few formulas to model thermal radiation. The first one's Stefan's law, which basically models how much thermal radiation anything emits. There's a constant delta, or well, sigma there, the Stefan-Boltzmann constant. The amount of thermal energy you emit increases with the surface area. And there's a third term there, E, which is not the exponential function, but it is the emissivity of the surface. Essentially, how good are you at releasing thermal energy? Theoretically, nothing is a pure, absorber emitter, except a black body. So a black body has an emissivity of 1. It's really good at emitting thermal energy. In the real world, this value E is obviously less than 1. And then T is just the temperature of the object, of the person, in kelvins. And finally, there seems to be a peak in the intensity of thermal radiation, and that's based on Wien's displacement law, which tells you for what wavelength, for where it is in your thermal spectrum, tells you what the peak wavelength is going to be in intensity based on the temperature. So this implies that for hotter objects, the peak wavelength is shorter, meaning that thermal radiation has a peak at a lower wavelength. So it's radiating energy of lower wavelength, which means higher frequency, which is why as objects get hotter, as you see in the drawing here, they tend to, they start off emitting, infrared radiation, then they give off more and more radiation in the visible spectrum as they get hotter. Theoretically, if you kept hitting a metal, it'd start to give like ultraviolet thermal radiation and eventually give out X-rays. However, by the time that the temperature is so high that the metal's in that state, the metal will break down. Other things will begin to happen. But within 1,000 or so Kelvin, the metal remains intact and just simply emits a glow. And then to properly model this curve, which was observed experimentally, you couldn't do this with classical physics, because classical physics would predict that the curve would just go off to infinity for the lower wavelength light. So the curve predicted by classical physics kind of goes up like this forever, but clearly, observationally, the peak happens somewhere in the middle between short wavelengths and big wavelengths. So it wasn't until Planck came up with his theory of particles having discrete amounts of energy and radiation happening when they jump between energy levels that he came up with a formula to describe this intensity properly, which is shown here. And so if you kind of plot this intensity function follows observations pretty well. basically the peak of the intensity curve is centered around the temperature. So this will shift to the left as temperatures get hotter, as seen in the experiments. And now we introduce a very important constant, which is Planck's constant. It's not something you have to memorize, but it's a good form. It's a good number to know. You have to like remember 10 constants in physics. This will be one of them because it's going to show up in basically everything we do in quantum mechanics. Anyways, for classical physics, they develop a formula for the intensity called the Rayleigh-Jeans expression. This formula, well, it doesn't really follow the observational data at all. It does work for long wavelengths. So if you take the Planck formula, which is more accurate, if you are dealing with the intensity of long wavelengths, then you can actually use the Rayleigh-Jeans expression. It's fine. It's just that at short wavelengths, this one doesn't really work. I wouldn't expect you to memorize this formula. Obviously, it's just something you could plug. Anyways, so yeah, quantum mechanics is able to explain black body radiation a lot better than classical mechanics could. Same thing with the photoelectric effect. To summarize, it's an experimental setup where you have two plates inside the vacuum tube to kind of maintain a vacuum in that region, and you can shoot light into one of the plates. Let's call that the ejection plate. And if conditions are met, you can actually get electrons ejected from the plate into the other one. So they'll travel to the other plate called the collector plate, and the battery that's attached to this whole circuit here is set up so that the collector plate is positively charged and the ejection plate is negatively charged. So it means that the electrons that get ejected do want to go to the collector plate. So this potential difference here is much like a downhill slope for the electrons. They're happy to go to the collector plate. And in doing so, they'll actually travel through the circuit back to the ejection plate. And in doing so, you will register a current. Because the electrons are getting ejected from thanks to the light hitting the plates, we call them photoelectrons, and we call the current that they produce a photocurrent. So classical physics thought that light being a classical wave, you needed just to shoot intense light into the electrons to essentially cook them faster, to cook them hot enough to escape. But it turned out that light doesn't behave like a classical wave. It's not the intensity that determines the energy, but rather the frequency. So as you can see here in the drawing below, it's showing you how shooting red light that has a energy associated with its frequency and its wavelength. After all, wavelength and frequency are paired together. Basically, you always have the formula, the speed of light is equal to the wavelength of light times its frequency. So every wavelength corresponds to a particular frequency. But anyways, so this long wavelength light has a small enough frequency, and as it turned out, as Einstein developed, the energy of light is proportional to its frequency. So this is not enough energy to eject an electron. But at some point, you can increase the frequency of light. So if you shoot blue light or purple light, that does eject electrons. And the more energetic the light is, the faster the electrons jump out. Note that as light gets more energetic, from red to blue to violet, its wavelength decreases. Anyway, so Einstein developed a theory that the light behaves as these particles called photons that carry a discrete amount of energy equal to Planck's constant times the frequency of the light. And he figured that the way that they interact with the plate is that one electron absorbs one photon at a time and either uses that energy to escape or throws all away. So they can get enough energy from one photon to escape the plate, overcoming what's called the work function of the plate, And so whatever energy they have left from the absorption is going into their kinetic energy. And the work function is a property of the metal of the plate they're stuck on. So there's a table there that shows you how different materials have different work functions. But basically, it doesn't matter how intense the light is, you need light of a particular frequency above some threshold to eject electrons and get them to reach the other plate. And while you're at it, you can figure out that there must be then some cutoff frequency, the lowest frequency possible for you to register a current. You can figure that out based on the relationship between the kinetic energy of an electron and its work function, which basically you're saying that at the cutoff frequency, you just have enough energy in the photons to just eject the electron. So all the energy goes into ejecting the electron, which means all the energy goes into overcoming the work function. So all the energy from the photon goes into the work function. And so from that, you can figure out what the cutoff, what the threshold frequency is. And then you can also calculate the wavelength of the photons because you know the frequency and you can calculate the cutoff wavelength. Because a lot of these energies are for particles and the work functions are in electron volts, it's more useful to deal with Planck's constant rather than joules per second. It's better to deal with it using electron volts. So it's worth knowing that when you have Planck's constant, the speed of light, that's equal to 1240 electron volts per nanometer. So the units are set up this way because a lot of the time the wavelengths are in nanometers. So this formula just makes using this in electron volts per nanometer reduces the number of unit conversions you have to do while solving problems. Anyways, what's shown on the graph on the right here is simply that it shows you what happens to the kinetic energy of the photoelectrons as you increase the frequency of the light that's hitting them. And no matter what kind of metal you're using, there's a sort of linear relationship between the frequency and the kinetic energy. More frequency means more energy. But there's a minimum frequency for which they'll actually jump out, and that's the cutoff frequency. Right, so here I'm just summarizing what the classical physicists thought, what they expected to see during their photoelectric lab. And, you know, basically they thought that light being a wave, its energy dependent on its intensity, not in its frequency. But then they realized that, no, wait, hang on, if the frequency is too low, we won't see any current. They thought that the kinetic energy will increase with intensity. That didn't happen. They thought that frequency didn't matter, but it did. And they thought that it would take some time between turning on the light and registering a current because the light was kind of like slowly cooking the electrons until they had enough energy to pop out. But interactions seem to happen right away. They turned on the lamp and current was read right away. So Einstein explained all of this. Basically, the energy of the electrons doesn't depend on intensity. It turns out it depended on the energy of the photons. If it's enough to overcome the work function and whatever is left goes to kinetic energy. They found that even at low intensity, electrons were emitted because as long as you were above the cutoff frequency, you would emit electrons. And they found that, yeah, there's a cutoff frequency, and that's because photoelectrons only absorb one photon at a time. So from there, that photon needs to have enough energy to overcome the work function. And they did see that as they increase the light frequency, sorry, the light intensity, that does increase the current because more ejections are happening at a time. But again, it doesn't increase the kinetic energy, only the change in frequency does. Okay. So yeah, we'll do some questions now. Let's look at this question here. You are setting up a photoelectric setup. You're shining light into a sink surface. So one of these statements is true. All other four are false. So maybe I'll give you a minute to read through them and just kind of maybe write down the one you think is true, and then we'll discuss. Okay. Well, let me go through the questions. One of these statements is true, or the rest are false, right? So let's see. First one says number of photoelectrons emitted per second is independent of the intensity of light for all different wavelengths. Okay, so this one basically says that intensity has no effect on photoelectrons emitted per second, and that's actually not true, because more intensity means more interaction. So you would see an increase in current if you increase intensity. Okay, B says the number of photoelectrons emitted per second is directly proportional to the frequency for all the different wavelengths. So this is basically saying that the number of electrons emitted per second is proportional. It's kind of saying that, like, basically, essentially, the current produced, the photocurrent, is proportional to the frequency. But this is also not true. So the frequency kind of determines whether electrons can get ejected or not. But even then, the relationship between, the energy of the electrons, the speed at which they get to the plate, is like a linear relationship with the frequency. So it's not a direct relationship between, the speed of the electrons and the frequency. It's a linear one, so this isn't quite right. Statement C says the maximum kinetic energy is directly proportional to the frequency for each wavelength present. Again, the keyword here is directly proportional. Directly proportional implies this, but it's not quite right. Again, it's actually a linear relationship. So it's not true. D says the maximum kinetic energy of the photoelectrons has a linear relationship. Yeah, that's a linear relationship to me. So this is true. And E says, well, that the maximum kinetic energy depends on intensity and independent of frequency, and that's not true. That's what classical physics will lead you to believe. Okay, so yeah, the answer is D. Okay, one more question. Photoelectrons are ejected with monochromatic light. So monochromatic just means it's all one color, one wavelength. And you want to increase the current, essentially, photocurrent. So what do you need to do? I'll give you a minute to think about this one. So think about, changing what can change the rate of interactions. So if you were thinking about E, then you were correct. So basically, if you increase the frequency of the light, this only increases the kinetic energy, but it doesn't increase the rate of interactions. But B and C would increase the rate of interactions. Because more intensity means more photons are hitting the plate per unit time. And increasing, hitting a bigger area means that, again, more electrons will be getting hit at the same time. So it's E. Okay. So this question is asking for the observations made during a lab on the photoelectric effect. And one of these observations can only be explained with quantum mechanics. Or maybe it's all of the above. So it's either one or one of these four or all of the above. So maybe take a minute to think which one can be explained only with quantum mechanics. Or maybe it's all of them. Hmm. I'm realizing now that it should say on light intensity. Okay. So if you're thinking B, you're correct. Basically, you're looking for an option here that cannot be explained by classical physics. A, C, and D all don't really have any notion of quantum mechanics in them. Because A talks of an intensity, which classical physics, thinks of light as a wave, so intensity is still valid. C talks about the work function of the metal. That's not really quantum mechanics; it's just particle physics. And D talks about the stopping potential used to measure the kinetic energy. That's just based on conservation of mechanical energy. You don't need quantum mechanics to explain that. How if the stopping potential is big enough, the kinetic energy of the electrons, will not, it won't be able to be big enough to reach the other plate if the potential is really strong. But B talks about the kinetic energy being related to the frequency of the light, which is something that only quantum mechanics can be explained. So the answer is B. Okay. Does anyone have any questions with the for the electric effect? Okay. Well, in that case, I'll show you some problems. A lot of the questions you'll have to just figure out cutoff frequencies or kinetic energies and such. So just be careful with electron volts and joules. In this question, you're told about the work function of the surface. It's a photoelectric effect setup. You know initially there's a photoelectrons with a maximum kinetic energy of 2 electron volts. And now you're told that the frequency of light is doubled. So the frequency, whatever it was, is now twice the old frequency. And the relationship between all this, because you're trying to find the maximum kinetic energy, then consider that basically what you have is the Einstein formula, which is always what we're going to use for pretty much all these questions. So despite the fact that quantum mechanics is a little bit tricky, the formulas are not too bad so far. Anyways, the relationship again is maximum kinetic energy is however much energy you get from the photon minus the work function. And the only thing you really know now is that the frequency has changed, it's been doubled. And so whatever energy we get from the photon, it's twice as much energy, right? Because the energy of the photon is directly proportional to the frequency. So if you double the frequency, that means the energy is also doubled. So then in this case, if you look at the initial, if you look at it initially though, initially you had 2 electron volts of max kinetic energy. That must be equal to the initial energy of the photons minus the work function, which is 3. So then you can actually find the initial energy of the photon this way, which would be with some algebra 5 electron volts. And now you're told that you doubled the frequency. So that means that the new energy of the photon must be also doubled. So we have 10 electron volts of frequency, photon energy. So if you plug that in, you get that the max kinetic energy is 7 electron volts. And that will be it. Okay, this is a thermal radiation question. You have a body temperature because the
book was written by an American author. It's in Fahrenheit. Assuming your skin is a perfect radiator, your emissivity is 1, determine the wavelength corresponding to the largest intensity. So for this, you can use Wien's law, which it's not something I expect you to memorize, but basically it tells you the peak intensity, the peak wavelength for a particular temperature. And we're going to use that to figure out that's not the right question. There we go. We need to find the wavelength, right? So wavelength max temperature is equal to 2.898. What do we send to a -9? Even I can remember the formula. 2.898 times 10 to the -3. Note the temperature is done in Kelvin, so we have to convert Fahrenheit to Kelvin. Basically, I guess you can do this with like Google, but the conversion between Celsius and Fahrenheit is that 1.8 Celsius plus 32 gives you the temperature in Fahrenheit. So you can work this out backwards to get the temperature in Fahrenheit minus 32 divided by 1.8 gives you the temperature in Celsius, which for 98.6, this is roughly, I believe, 33 degrees, I want to say. 37 degrees Celsius. But we're not done yet though, because we need to convert to Kelvin. So the temperature in Kelvin is the temperature in Celsius plus 273. And so we would get 310 degrees Kelvin. Finally, we can then find the peak wavelength by just taking the Wien's constant here, divide that by the temperature we have. So at this point, we're just plugging in algebra. Because we are talking about our regular body temperature, 37 degrees Celsius, we should expect the max wavelength to be somewhere in the red infrared spectrum. Anyways, so you do 2.898 times 10 to the -3. Divide that by 310 Kelvin. What that should give you is, let me pull out my calculator. I usually like to write out the formula a little bit ahead of time, but it's 2.898 e to the -3 divided by 310. So that gives you 9.3 10 to the -6 meters. And the answer wants to be done in micrometers. So to do that, you need to remember the conversion between meters and micrometers. So in basic units, SI units, the max wavelength is 9.35 times 10 to the -6 meters. And then you want to get that in micrometers, so you have to do a unit multiplier that. Basically, 1 meter is equal to 10 to the 6 micrometers. So this should get you about 9.35 micrometers, which is about answer B. Okay. The threshold wavelength for the electric emission of a particular substance is 500 nanometers. What is the work function? So keyword here is threshold wavelength. So if photons have a threshold wavelength, they have a corresponding threshold frequency. We can relate the two using the wave equation. So the threshold frequency, you can get that using C or lambda. But you can then, but because you're trying to find the work function, you can actually write the max kinetic energy formula in terms of the cutoff, cutoff frequency. So what I mean is, when you have the cutoff frequency, right, the kinetic energy at 0, the electrons just barely get ejected. And you're given a cutoff wavelength. So you can find the frequency, or you can just use the wave formula inside your equation here. And so you're able to find the work function in terms of the two constants h and c divided by the cutoff wavelength. So just, you can always take the fact that h times c is 1240 electron volts times nanometer. You can use this because a lot of the wavelengths are given in nanometers anyways. And so you can get an answer for the work function right away without having to do electron volts to joule conversions or anything like that. So if you do that, have 1240 divided by 500, you should get about 2.5. And right, you can always keep track of the units. Okay. So we'll do one more question. What is the maximum velocity of a photoelectron emitted from a surface whose work function is 5 electron volts when illuminated by a light whose wavelength is 200 nanometers? Okay. So this one's a bit tricky. We're asked to find the maximum velocity. And that's kind of interesting because we only really been dealing with this formula for the photoelectric effect. And if you look at the formula, though, it does give you the max kinetic energy of electrons, right? So for an electron, its kinetic energy would just be the same formula we'd seen in classical physics, 1/2 mv squared, right? The electron has a mass, has some velocity. So we can then figure out what the velocity should be based on that. We have the wavelength of light, so we can actually write this formula in terms of wavelength. We know the work function is 5 electron volts, so that would give us wait, that's nanometers. So I'm dividing by the wavelength of light that's illuminating the plate. That tells you how much energy the electron gets minus the work function 5 eV. So this fraction is 6.2, and we get 1.2 electron volts, which will be the max kinetic energy of the electrons. So we can now say we can use the formula for kinetic energy here to get the velocity, knowing that kinetic energy is 1.2 electron volts. However, mass is in kilograms, velocity is in meters per second. So to properly work this out, we need to convert the kinetic energy that we found to joules. Because if we don't do that, the units will not work out. So 1.2 electron volts needs to be in joules to find the velocity. So remember, the conversion between electron volts and joules is that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, which will give us 1.9 times 10 to the negative 19 joules. Great. So now we can find the speed of the electron. There's a square. Don't forget to do a square root at the end. But basically, if you do the algebra all in one, you get 2ke over m. And that would give you a bit of a mouthful, times 1.9 times 10 to the negative 9. Wait, it's 10 to the negative 16, not 19. Actually, can anyone double check on this? Is a joule, is it 1.6 times 10 to the negative 19 joules or 10 to the negative 16 joules? Anyone know?
I think it's 1.6 times 10 to the negative 19 joules.
Awesome, thank you. 19. So And then you have to divide the mass of an electron. This is a number worth memorizing. I don't expect you to memorize it, but you should know that the mass of an electron is tiny. It's 9.11 times 10 to the negative 31 kilograms. So if you plug this all in and you take a square root, so actually, you know what? I'm gonna do it right now. I'm gonna go on my calculator and do it to show you, e to the negative 19 divided by 9.11 e to the negative 31. You should get about 650,000 meters per second. And you're asked to find to make it to kilometers per second for the answer. So if you want to do kilometers per second, you just bring it down. You kind of take off 3 zeros basically and call that a kilometer, because 1 kilometer is 1,000 meters. So it's fast. 650 kilometers per second is fast, but it's not relativistically fast. Don't assume because any particle is small, it's necessarily going to be moving at relativistic speeds. Anyways, so all the questions we'll do today kind of follow this kind of similar pattern. How are we doing? Maybe give me like a thumbs up or a reaction. If we're doing fine so far. All right, I'm seeing 2 thumbs up. So I'm assuming that only 2 people, 3 thumbs up. Okay, so 3 people understand quantum mechanics. Oh, 4. Okay, that's 4 people. Well done. I still don't understand it, so I'm not gonna give a thumbs up. Actually, that's not true. I'm gonna give a thumbs up. I like giving a thumbs up. Yeah, but you're gonna have to do some questions related to the photoelectric effect for the 4th assignment. I'm putting it up later today. So if you have any questions about the assignment, you can ask me. You can let me know. Yeah. Anyways. So this question is actually the same as the last one, which is asking the maximum kinetic energy, which we already found is 1.2 electron volts. This question right here is new though, so let's take a look. Okay, you're told about the light intensity on a metallic surface. It's ejecting photoelectrons. You're told the max kinetic energy, and you're told that the light intensity is doubled. Find the new kinetic energy. So don't say it out loud. I'll give you like 30 seconds to think about this. And then we'll discuss it. So you're told the maximum kinetic energy originally is 2 electrovolts. And then you're told that the intensity gets doubled. How does that change the max kinetic energy? Don't think about it. Okay, so based on what we learned about quantum mechanics, does the intensity of light, does it determine the energy of its photons? Yes or no? What do we think?
Yes.
So the intensity of light determines the energy of the photons. So it turns out that the intensity of light determines the amount of photons that are being emitted of a lamp, of the light source, of the laser or whatever, but it doesn't determine their energy. Each photon carries a discrete amount of energy determined by the frequency of the source. That's why Einstein figured out that the energy of a single photon in a beam of light, and again, photons and lights, I'm using the term interchangeably because photons represents what light is made of. So a single photon in a stream of light, its energy is proportional to the frequency. There's no relationship between the energy of an individual photon and the intensity of the light that's emitting it. After all, then if we consider the formula for the maximum kinetic energy of the photoelectrons, we see that there's no mention of intensity. It only mentions the frequency of a single photon of the light, which has the same frequency as all the other photons, and the work function of the metal. In other words, there's no relationship between maximum kinetic energy and intensity of the photons. There's only a relationship between the frequency of the light and the kinetic energy of the photoelectrons. Does this make sense? Will anyone like me to repeat the explanation? Okay. So intensity has essentially no effect because it doesn't determine the energy of the photons. The photons, their energy is determined by the frequency. And if that's not changing, neither will the energy that the photoelectrons absorb that gets converted into their kinetic energy. So then that means the kinetic energy does not change, which means that the answer is the same as the initial, which is 2 electron volts. Okay. So that's about all the time we really have for today. So you can see how this questions, this formulations are not necessarily too tricky. I'd argue that the theory behind them is a lot harder than the problem solving, right? We don't really need to know the theory of quantum mechanics to plug in this formulas to figure out the maximum kinetic energy or whatever. So at the very least, it's manageable. And what am I going to say? Right. So yeah, I'm going to put up the fourth assignment later today. It's going to have questions related to relativity and some of this stuff with photoelectric effect. Then the last 2 assignments will cover the rest of the chapters, including atomic physics. And I'll mark your second midterm sometime this weekend, as well as your third lab reports. There's still 1 more lab left to go. We'll do that in 2 weeks. And yeah, otherwise, if you have no further questions, you can always just email me in the future questions on the assignment or whatever. And yeah, otherwise, I'll let you go. I wish you all a good one, and we'll see you on Friday.
Thank you, sir. Have a good day.
Yeah, thank you. You too. I usually go till 11 a.m. So this is my attempt to not go there. So 10:54. I'm doing better. Okay, well, no further questions. So I'm going to take off. Again, I wish you all a good day, and we'll see you on Friday.